the second part of the lecture given by Professor Burkard Hillebrands from Rhineland-Palatinate Institute of University of Technology. Yeah. So, please.
Yeah, so thank you. Well, we know each other from yesterday, so no big introduction. Yeah, the difference between yesterday and today is yesterday was the fundamentals, and now today, as promised, somebody said the cliffhanger, yeah, is now the applications. I will stay within Bose-Einstein condensates. That is different from that what Andre and many of you are doing, just to show what the potential is. And I think the most important thing, the most important message, what you should have taken home yesterday is that magnonic BECs are carriers of macroscopic wave functions. This sounds very esoteric, but you know, a wave function is very often used as a quantum mechanical object. It's not intrinsically a quantum mechanics. You can also have classic wave functions. This is a classic wave functions. And that is different from particles such as electrons, protons, and so on. But you know that de Broglie showed us how to translate particles in waves and vice versa. So the best thing is always to think in both quantities. And if we talk Bose-Einstein condensates, that was the key message of yesterday, is think about these particles which undergo Bose-Einstein condensation as waves, and you describe the ground state of the system where all the particles collect. You're noticing I'm mixing now two different ways how to express these things. You have to consider it as a macroscopic wave function. And waves are nice because waves have interference and they have a lot of other interesting properties, polarization, for instance, and that is very useful. You see a long list of items. I would like to go through it. I don't want to disturb you too much with this geograph, but simply take home here from this list. We are discussing primarily transport. We want to do something good with it. I like to say, if we study a system like the dispersion of spin waves, it's always a boring system as long as it is in equilibrium. Yeah, the fun only happens if you go to a non-equilibrium state. Yeah. If you have transport, electric transport is maybe the most simple example. You all know, I mean, if the light goes on, of course, that is a non-equilibrium state because you have a space where you have many electrons, another space with little electrons, and therefore, now discussed in a very complicated manner, you have a flow of electrons which generate light, heating, noise, whatever it is. Yeah, same here. But we can have transport, we can categorize transport in two different areas. One is just real transport from here to there, or transport in reciprocal space. And this gives us an additional degree of freedom, and you will see why this is so interesting. I will start with intellectually more simple case, that is transport in real space. So how do Andre and I communicate via Bose-Einstein condensate? So that is the question behind, and I will start to show this, and you will find very, very interesting things here. Let's get started. So just to repeat what we discussed yesterday, let me quickly go through it that you all have not forgotten any details. Number one, a BEC is a macroscopic quantum state. We discussed that. The fundamental scattering processes, or in other language, the leading nonlinearity of the system is 4 Magnon scattering. You remember we have a gas of Magnon. We call it a gas because it acts like a real gas. 2 incoming Magnons, 2 outgoing Magnons, a scattering process in between, energy and momentum conservation. So these conservation rules help us to understand it. We can really think of them like gas molecules in the atmosphere. The problem is, if we have that, we generate a lot of excess Magnons, which shouldn't be there in a certain area of the spectrum, and they cannot relax within the system relaxation time. And if we have that, then we describe the little degree of non-equilibrium of the system by chemical potential. Yeah, it's just a trick to have a very convenient way how to describe non-equilibrium properties. The order parameter is coherency. I think you all have digested because I spent so much time to show you how to measure coherency, and that the coherency indeed is spontaneous. It's not an implied coherency. Ferromagnetic resonance, for instance, is always coherent. Yeah, but that is an implied coherency because you lock the system to your microwave generator, which by definition is coherent because it's just an oscillator. Yeah. And we discussed several methods how to generate a BEC, to generate the coherency. The most important was parametric pumping, but we also looked into other ways, such as spin transfer torque or rapid cooling. And so you could see that. And just to repeat what happens if you do parametric pumping, we have microwave photons at a certain frequency. We call it the pumping frequency here. A photon decays into two magnons. They have half the energy or half the frequency for energy conservation because from one particle we now have two. They have opposite wave vectors here. You see that? That is a wave vector scale. That is a frequency scale because the microwave photon on this scale have negligible wave vector. It's negligibly small because the velocity of light is so large. Yeah, and then these four Magnon scattering processes, which you see here, they set in and you have all these many scattering events symbolized by these little arrows you see here. You get an incoherent gas of Magnons, and finally they will condense into the lowest energy state, which is just here at these orange points. And we have them at a finite frequency because we have the backward volume modes, which you see here. And here you see the onset of the exchange interaction. So dipole-dipole interaction plus exchange interaction create a minimum at a finite frequency, and that is what we use. Okay. So that is basically what we use. I like to introduce a new word. I think if we discuss politics, I mean, how do we shape science? How do we sell science to our colleagues? It's always good to come up, not to invent, but to come up with some more general idea how to describe it. Yeah? And one is accumulation. Yeah, I mean, accumulation simply means here, yeah, you know what accumulation is. I can accumulate money, yeah, and then my pocket is very big, yeah. That is very simple. But what we can do, if we have the dispersion you just have seen, we can think about processes. How do we bring Magnons to a certain region in the dispersion, certain frequency range, certain wave vector range, and that we call accumulation of Magnons. Yeah. And if we master that, if we know how to do it, we can do a lot of things, as you will see in what I'm showing to you. So accumulation phenomena is we call it the spontaneous accumulation of quasiparticles in spectral regions, different from the regions of initial excitation of such particles. Yeah, and with all the many words I already used, you see there's transport behind, yeah, because I make them here in a diagram, whatever the axes are, yeah. And now I look, what is the accumulation doing here in that area? How do they make their pathway from that area to that area, in a very general sense. Good, so we have many, many examples, and I'm going through these examples now in this lecture in particular. One very trivial way of accumulation, of course, is Bose-Einstein condensation, because all the Magnons accumulate at the bottom of the spectrum. This you have learned. Yeah, I think that is nothing new for you anymore. Yeah, we have more. There's something called kinetic instability, which is a highway to the condensate. I will show you what that exactly means. Yeah, long time known before Bose-Einstein condensation in a magnonic system has been seen. Yeah. I will show you virtual Magnons, which you can generate. That is again a new term. I have to explain what that is. And you do not only have Magnons in our system, we can have many other excitations such as phonons. They can couple. And a very interesting case is Magnon-phonon accumulation, which actually bears a very large technological relevance. I will discuss that. So that is what I would like to show you. So let's begin with a very simple transport mechanism that is Magnonic supercurrents. You all know what supercurrents are in an electric system. You have to have a superconductor, you have to cool it down. If you are very lucky, you have a superconductor which you only need to cool down to liquid nitrogen temperatures, but you cannot do it at room temperature. And then you can have currents flowing without resistivity. And that is, of course, a very efficient way if you think about Maglev trains, for instance, and many, many other applications. I will show you that the same thing also exists here in our world, in our magnonics world. So let's discuss it. What is a supercurrent? Well, it's very simple. All you need to know is this one formula which you see here on the right side. Let's see what we have. We have the wave function of our Bose-Einstein condensate. It's a complex wave function. We call it simply psi. It's a function of the space and a function of time. Yeah. And we can calculate the density, which is nothing else than the number of our Magnons. It's a particle picture, nothing else than just the square of the amplitude. And of course, if we have a wave function, we also can calculate the phase. The phase is nothing else than just the arguments, the real part here of the wave function. Yeah? That is what it is. And the supercurrent we now borrow from superconductivity is nothing else which is just driven by the gradient in the phase. Yeah? Gradient in the phase, nothing else. And you need a few parameters in addition, h bar, and the mass of our particles. In this case, is the mass of our magnons, and a parameter which is just the critical number of particles you need in order to have that. And now comes the most difficult part of my entire lecture, because I have to show you a simulation, not on the view graphs. Think about two spins like this, yeah? And now you want to have a Magnonic supercurrent. These are, of course, Magnons, yeah? Call it ferromagnetic Magnons. It's the most simple case, yeah? You have these Magnons, okay? And now you want to have a supercurrent. How can you make a supercurrent? Recipe is at the whiteboard, yeah? You have to get a phase difference in between. How can you create a phase difference? Question to you. Yeah, how can you make a, does it work? Any problems? Yeah. How can you make a phase difference? I will show you. It's very simple. You just have the two magnetic moments which are precessing, and you simply let one moment, I have to try again. You give me 3 tries, yeah, because it's so hard to do. Yeah. So again, so you're just precessing in phase, yeah, and now you allow one moment to precess faster, yeah. Do you see that? My left arm from your side, my right arm is precessing faster, yeah? Can you, with your eyes, measure the phase between these two spinning magnetizations? Can you do this, yeah? You see there is a phase difference here in between, yeah? And it is constantly increasing in time, or decreasing. It depends on which kind of difference you take between these two spins. Yeah. So we are in business, so we are here, yeah? You see here the phase difference. You see here the phase difference, just delta phi, or if you are in a three-dimensional space, it's a gradient. Yeah, and that's it. So we have our recipe. We need to have our precessing spins, and of course, for that, we take our Bose-Einstein condensate. And now what we need to do, we need to make one part of the condensate precess faster. And you all know how to do this. You all know about ferromagnetic resonance. Ferromagnetic resonance simply means if you have a precessing moment and if you increase the field, it precesses faster. So the recipe is simply, why not making a Bose-Einstein condensate, but do it in a field gradient. Yeah, then the internal field here is, let's say, larger than there, and we constantly have a phase difference here in between, and we should get a supercurrent, so we get transport. Yeah, this is very simple recipe, and it is dissipationless transport. Yeah? Yeah. It is dissipationless transport. We can transport energy without any losses, with the remark that magnons always have a finite lifetime. They will not overcome it. But I will show you. I mean, the record holder, we were mentioning it yesterday, is sitting here. Rostislav is the record holder. I will show you actually a little trick later on, how to even more to decrease the damping. Yeah, there's a little trick behind. I will show you. Okay, so we talk about the accumulated phase. The accumulated phase is nothing, you take this formula, is nothing else than just taking the difference in the frequencies, multiply it with the time, and then you get a phase difference. Yeah, very trivial. So that is the accumulated phase. So what we need to do is exactly what I was just explaining. We need to change the local frequency of the BEC, and this leads us to a new concept which we call now thermal landscape. And I will show you what that is. That is the setup. I always like to discuss setups because there are so many ideas in it. If you understand the setup, you have understood the entire idea. This setup has 3 parts. Number 1 is we need a sample. Here is a sample. Yeah? Number 2, we want to do, of course, Brillouin light scattering. Yeah? So we have this green part, so we have somehow a laser light which is shining on the sample. We collect the back reflected light, and we send it here to a Fabry-Perot interferometer, which is not shown here because you all know what Fabry-Perot interferometers are. And now we add something else, and that is actually here a heating laser, just a laser, and we put it on a special device which is called a spatial light modulator. Spatial light modulator is just like a DR or something like else. And it reflects the light, but you can locally change the reflectance what you have here. That is shown here with a checkerboard type of thing. Then we focus this light here onto the sample with this lenses. We also have a beam expander, but that is only a little detail. And what we can do in this case, we can create any kind of pattern on the sample surface. Here, for instance, you just see a pattern which consists of two dots, here where we focus the light. What we actually do is nothing else than a projection, and we put the spatial light modulator in the Fourier plane. You know, if you take an image with a lens, you have obviously the real planes and you have the Fourier planes. And if you do the Fourier plane here, then you just, by a computer, apply a Fourier picture of that what you want to project, and then you get a very nice projection. These kind of devices are built into modern overhead projectors, for instance, because they are very fast, very efficient, very high dynamic range. So that is a common technique. So we have the system here, and what you can do, oh, this was too fast, you can, oh, this is now too fast, what is that? You can create any kind of picture you want. For instance, we can also project the logo of Kaiserslautern University onto the sample if we wish so. And once again, just the important stuff is we have three components here. We create the thermal landscapes with this light. We do spin wave generation just by connecting it to a microwave generator. And we do spin wave detection here with this green path with the light. So you got all the information, And you see now we have exactly now an experimental setup where we can study what we were just discussing. We can create temperature gradients. We can create Bose-Einstein condensates, because we only have to apply here the microwave frequency of the pumping magnons for parametric pumping. So we can put it all together here in this experiment. You got it? Yeah, it's clear, because this is not important for the next book. So, for instance, what it comes, since many of you are Brillouin light scatterers, I will show you a few tricks which work very, very well. For instance, what you see here is just a sample. Here is a microstrip resonator connected here to a microwave generator, and we use that for parametric pumping. We have two spots here in blue, which are just made with a spatial light modulator. That is a projection technique I was explaining. And we use it to locally heat the sample. And if we locally heat the sample, we reduce the saturation magnetization. So the inner field is changed. Okay? So, and then we do Brillouin light scattering with a probing laser. The Brillouin light scattering light is always green, just by definition. Also, you might have a blue laser in your lab. Okay, I'm joking here. And now what we want to do, of course, we want to do space-resolved Brillouin light scattering. So what we need to do here is a laser spot. So we need to scan here across the sample. And if I would tell you as a student, oh, please do this measurement to you, you would probably protest very seriously, because you don't know how to do it. You don't know how can you move a laser spot across a sample. You're always measuring at the same point. It's much easier to move the sample around. In this case, you don't need to change. Sorry, you're shaking your head? No, okay. Okay. In this case, you even don't need to change the sample position. You can do much easier, because you are projecting here these two blue spots where you heat the sample. You can simply let these two spots move across the sample. A very elegant way to now to do the experiment. This should be some inspiration for you if you're doing this kind of Brillouin light scattering experiment. So let's see what happens now. I will directly jump to the results. We have two heating spots on the sample. I was mentioning that in this case we should generate a supercurrent, and now I will show you the evidence for the supercurrent. This view graph here is very busy now. What you now have to take into account is, so each line is a measurement, and between these horizontal lines we change the separation of the heating spots, and the heating spots are exactly where this red line is. So in this experiment the heating spots are here and there. Here they are a little bit more apart, and here they're even more apart, and so on. And here the distance between the two heating spots is very large. And now what I will show you how the time development happens. So look at it. It will be very fast. Oh, sorry, before I start that, just the scale. So white means reference, no heating. Red means, of course, it becomes hot. Yeah, and blue means it becomes cold. Cold means you are lower in intensity than in the reference case. And now let's see. Is it moving? Yeah, now you see what is happening. We have to wait. You see the time running here in nanoseconds. And now after a while, you see something very interesting. Do you see that? Here, where we have the heating spots, it becomes colder and colder. So we have less and less magnons there. We are measuring the magnons here with Brunner light scattering. And here in the area in between, it becomes hotter and hotter in terms of the number of magnons. So what you observe here in the raw experimental data already is obviously a transport of magnons, because we are shuffling magnons from these blue areas to the red areas here. Yeah. You see that, Andre?
There was a paper where people have shown that BLS intensity, scattering efficiency decrease with increasing temperature.
Yeah.
Did you take it into account that it's not because of the
No, because the temperature changes are very small, so we can neglect this effect. Yeah, but you're right. I mean, because scattering efficiency goes with the magnetization, of course. Yeah, and if you change the magnetization, you also modify the scattering efficiency. That is correct. Yeah. But here the changes are very small. Sorry?
So the temperature changes are small. How large are they roughly?
We are talking a few centigrade. Yeah, we are not talking about 100 degrees. Okay, so you see this? So we get a redistribution of the spatial Magnon densities, and the only reason can be the supercurrents, because this is a condensate here, Bose-Einstein condensate we are measuring, and you have seen we have modified the condensate by locally heating the condensate with the lasers. So that is good evidence that we have it. We have seen this formula, so we have a supercurrent because the condensate is coherent all over, because otherwise it wouldn't be a condensate, what I showed you yesterday. And we have the accumulated phase, and now we obviously get the supercurrents here. And that is what we see in the experiment. So the supercurrents go away from the heated region. So here's the heated region, and so the supercurrents goes here away. Now come the problems. I mean, as a scientist, you always have to be serious. If we did this experiment, and if we now continue to discuss it in the way I was introducing it, we have a big problem, because the direction of the current is wrong. It goes into the wrong direction. I will now take you a little bit through the arguments, because there's so much to learn about it, how rich the physics can be. Let's take again, here's a dispersion, backward volume mode, yeah, a minimum here where the Bose-Einstein condensation happens, or the higher mode, so we have the Magnon gas here in between. And now what we can do is, we can of course ask, how does the frequency of the Bose-Einstein condensate change? And then you will see we have a big problem. Because if you change the temperature, if you change the saturation magnetization between 100 Gauss and 1750 Gauss, so maximum range, yeah, the frequency of the Bose-Einstein condensate will change nearly by nothing. Look at the frequency scale. This only changes in the second digit after the period. So obviously we have a problem. I was telling you rubbish so far, yeah, because heating the system does not change the frequency of the condensate. Something is wrong, okay? So what is wrong? Okay, I mean, what did we do? What we did, of course, we were shining with the heating, with the Brunner light scattering laser and with the heating laser here on the sample. That is a hot spot. Taking a thermograph, you see we have a very sharp hot spot here because we were focusing onto the sample, and that is how we were doing our experiment. Is there something wrong with the experiment? There's nothing wrong with the experiment, but there is something wrong with the way we understand it, and I will show you what it is. I will guide you now step by step through this. I don't want to be in your sight, so if I'm abstracting, you just tell me. Let's just step back a little bit. This is the dispersion what we had. Here's a backward volume mode. Here's a minimum where Bose-Einstein condensation happens. That is a backward volume mode. The wave vector is parallel to the field. We also have the perpendicular direction where the wave vector is perpendicular to the field. So that here is the surface spin wave. We have all kinds of modes here in between, depending on the propagation direction. And if we now do a Brillouin light scattering experiment without wave vector resolution, we would measure this area here. Yeah, many modes here because you have a nearly zero slope. Many modes here because, again, we have zero slope here in the region of the condensate, which means we accumulate a lot of particles there, and something here in between. So that is what we would theoretically expect. Okay, we can calculate the frequency. So this frequency, these are the well-known formulas. It's just given this one here. The minimum frequency is nothing else than just the external field. And now you understand why our heating didn't work. Yeah, because look at this, the external field doesn't contain the saturation magnetization. So if we heat the system, yeah, we do change the saturation magnetization, but the minimum frequency is not affected by that. So we have a problem here. I hope I'm not confusing you. I try to take you along. So what can we do now? Why is this not moving? Okay, but let's better look into the experiment. This is actually the experimentally measured with Brillouin light scattering density of states. And you see it resembles very nicely what we had in our calculation. Once again, if we really check what is happening, including full theory, full numerical simulation, we get this one here. So the minimum frequency is, even if you take, let's say, high-level numerical simulation, it is really constant yet. It changes very, very little. These are residual effects which you always have because of finite sample sizes and so on. So, but we overlooked something very important, and that is the following. The heating spot was very, very small. Yeah, the heating spot was very, very small. And if you have a sheet of paper, if I borrow a sheet of paper, I just borrow a sheet of paper, yeah, and if I now punch a hole in it, what will happen? Yeah? Very simple. Everything is magnetic, but not the hole. So what will you have? What will you have in the hole? Yeah, a lot of magnetic fields because you have the demagnetizing effects. You have the demagnetizing field. So if you make a hole, inside the hole you have the full field. Actually, that is often used in the design of magnets. If you look at it, you always take advantage of the demagnetizing effect, so you can achieve much higher fields than if you just only take the usual approximations. So what you have here indeed is you get strong demagnetizing effects. That is a hole. And here the effective magnetic field has been calculated. It's a very simple exercise you can do by yourself, but very easily by numerical simulation. And what you find is that if the whole diameter is very small, here is the radius in micrometer, and here's the demagnetizing effect, you can get very strong demagnetizing effects here, even as a function of temperature. And with temperature, the saturation magnetization, of course, changes, but these demagnetizing effects are very, very strong. So we have to consider these strong demagnetizing effects. And if you look into the experiment, here is what we get if we now heat. That is, blue was zero heating. Here, red or brown is heating with small power. And then if we increase it, then you see that indeed the minimum moves up. But why does it move up? Because we have the demagnetizing effects. And the demagnetizing effects depend on the saturation magnetization. Yeah, you see we have a crazy situation. The minimum of the condensate should not depend on the saturation magnetization. But that is only true for an infinitely extended Bose-Einstein condensate. But if we have a hole inside the condensate, yeah, because we were locally destroying the saturation magnetization, then all the surrounding areas which still have the full saturation magnetization, via their demagnetizing fields, yeah, they will create a strong demagnetizing effect, a strong field inside of this hole, and this will generate the shift what you observe here. So take care, it's a complicated system. No, sorry, it's a rich system. So we find that you can do now many things. You know, if we have that, if we know now the distribution of the demagnetizing field as the leading term, we can calculate the phase gradient, and then we have the supercurrent. And the supercurrents are very strong in the system. This is now a numerical simulation. So we have a supercurrent. So that is what the internal field is here, including the demagnetizing effects. It's of course asymmetric because we have the applied field here in the film plane, and we get supercurrents here in this perpendicular direction very, very strongly. We don't get the supercurrent in this direction because we need to have backward volume mode geometry for you. So we learned two messages. Supercurrents can be very strong, and they are very anisotropic. And now we can use it and play with this. For instance, here you see measurements now of the supercurrent. Here you see there's a BEC. It varies very slightly because of the demagnetizing effects, and here is a measured supercurrents where we can see as a function of time. So this is minus 250 nanoseconds, so where we were just grading everything, and now 20 nanoseconds, and then nearly 100 nanoseconds, and you see how it moves outside of the area. So supercurrents can be created. Okay, I was talking about supercurrents, and now a new term is coming in, which essentially is not very much different. That are Bogoliubov waves. Don't be afraid of the name. There's one little difference. If you have currents, again, we can switch. We can think of these currents as waves. Yeah, same game as before. And if you have a wave, you should immediately have two questions. Number one, what is the energy? Or in other words, what is the frequency? Frequency is clear. It must be the frequency of the condensate. And number two, what is the wave vector? Yeah, and the waves I was just showing you have nearly zero wave vector. But if that is the case, you can also create supercurrents with larger wave vectors. And they carry the name of Bogoliubov waves, or in other communities as second sound. Same thing, yeah? Second sound. Okay, measurements can be done. I will make it here a little bit shorter. Basically, what we can do is we can create a gradient. For that, we use a heating light spot here. Then with a BLS, essentially, we can scan across this line, and then we can measure it. Here you see the data. What you see here is a position on the sample as a function of time. And if you follow here, you see that something is moving out, and these are second sound pulses. One always likes to do it in a pulse regime because that is experimentally much better, because then we can really monitor the propagation. How can we understand it? Well, again, a little bit of formulas, but it is very simple. The framework is the Gross-Bitaevsky equation. You know, Heisenberg equation. Very, very useful. It has very little insight, but these are all the essentials. What is it is of course it's a first order differential equation with respect of time. What matters is the dispersion coefficient. So what is the curvature of your dispersion, and what matters is a nonlinearity in your system. That is this parameter W. Yeah, and that is the amplitude of four-wave repulsive interaction. I think you have another friend, Victor Lvov, who was here, yeah, and he invented the stuff. So we have to follow his definitions. Yeah. Okay. You can. I mean, if you take away the nonlinearity, you have a classical Schrödinger equation. Now, what we can do, we can solve it. So we are looking for stationary solutions. They all look very simple. What matters is you have an exponential term. It has in it the time, because it's a time propagation. It has in it a little bit here the nonlinearity, and the number of particles which you have here, the number of bosons which you have in your Bose-Einstein condensate, of bosonic magnons. And you have a prefactor, which is nothing else than just the square root of the number of Magnon particles, because if you square the wave function, of course you should get the number of Magnons in it. I think it's a trivial thing. Yeah, so you get it. So what you need to do, you need to solve this equation. The solution looks very simple, by the way. You can easily understand it, so you get solutions for these waves, for the second sound waves. I name them capital omega, just not to mix them with the omegas of our original Magnons. And then it looks like a nearly linear equation. You have a sound velocity, second sound velocity, Cs, the wave vector, and then the square root here from a term which contains unity, and then the ratio of the dispersion coefficient over the nonlinearity and the number of particles you have in the system. That just comes out if you solve it. It is a straightforward calculation. And if we see such equations as physicists, we know what to have to do. We have to take the two limiting cases. One is the long wavelength limit, that k is just very small. And then we end up with a linear dispersion. Omega is a function of the wave vector, and the proportionality factor is nothing else than the sound velocity. You understand why it's called a sound velocity, because omega is the same equation as if you would have acoustic sound waves. Yeah, just the same thing, looks just the same. And therefore we call it the second sound velocity. And the sound velocity is only a function of the nonlinearity and the number of particles. So you see the sound velocity changes with population. Yeah, you see that? So that is what comes out. Okay, of course we can check that in the experiment. So what we need to measure is just, for instance, how far does this wave propagate as a function of time for different heating powers. So these are 3 different experiments, and red means large heating, so large gradients, and green means low values. Then we can fit this data. We have to fit it with a parabolic equation. It looks nearly like a sound velocity, so linear slope. But since our Magnons have the problem that they have a finite lifetime, at the beginning of the transport, there are more Magnons than at the end, because some are dying in between, yeah? You understand? Yeah. So if we measure the propagation as a function of time, here you have less Magnons because of the finite lifetimes than here, and therefore, according to this formula, the sound velocity must slightly change. And you see that by the slight curvature here in the data. So it is there. So, yeah, you see a small decrease of the sound velocity. Okay, but if you really do it quantitatively, you see a decrease which is lower than what Victor Wolf was calculating to us. Again, another miracle. You see, we have a series of extreme interesting cases here. What is happening here? Well, hey, I don't have it here. What is this? Yeah, I'm very sorry, I don't have it here. But what is happening here? You have to imagine we have a condensate. Yeah, the condensate here is the entire table. You understand? Here we are creating pulses of the sound waves. Yeah. So these pulses propagate as second sound across the condensate. Of course, you can only propagate in the condensate. Yeah. The Magnons decay. That is, of course, a problem. So after time and time, we have less and less. And now comes the competition to Rostislav. But what these Magnons can do, they can still eat gaseous Magnons, because you have a background of gaseous Magnons. So the condensate can re-establish itself as part of the second sound waves. Yeah, so the damping is reduced. Unfortunately, we cannot fully compensate or even overcompensate, but if we measure the lifetime is much shorter than the lifetime according to the coupling to the phonon system, but what we always have. So, Rostislav, please do the same experiment at millikelvin with Bogoliubov waves, and you might even obtain self-sustained Bogoliubov waves, because the scenario should be much more favorable in your scenario. I don't know whether that is possible experimentally, but it would be a very interesting experiment. Okay. And now we'll switch. Is this clear so far? I have 2 complicated parts in my talk. This was the first and by far most complicated talk, because we had to put together so many different arguments. Okay, now something simpler. That is just Josephson oscillations. If you have Bose-Einstein condensate, and if you claim to have one, people are asking you questions. Show me Josephson oscillations. Very clear. Superconductivity and Josephson oscillations are very clear. You know what Josephson oscillations are? Yeah. you have a barrier in your superconducting material, and then you have a tunneling current. But since the tunneling current is coherent, quantum mechanically, if this is a barrier here, yeah, quantum mechanically this part and that part are coherently coupled. Yeah, via this weak link here in between. But if you describe it, you have a unique wave function for the entire object. You cannot separate it in two wave functions here and there. Yeah, they are coherent to each other. And then you get interference. Yeah, this is like the double slot experiment in optics. Just the same thing. So do we have it here? And of course, here I have really to take help from our this year's Nobel Prize winners, John Clark, Michael Devoret, and John Martinis, because they have really conducted a set of experiments with electronic circuits, not with magnons, unfortunately, and they have shown that the concept of macroscopic wave functions leads very, very far. Okay. So without their work, this work wouldn't be possible, what I'm showing you here. How can we realize it? I think we now have everything already here. It's a very simple setup. Again, we have yttrium ion garnet. We create a Bose-Einstein condensate. In order to create it, we have to throw into the systems the microwave photons for parametric pumping. Same story as we have it yesterday, and we had it at the beginning of my lecture. Yeah, but what we now do is just we modify the experiment a little bit. Again, here green is a BLS part. We monitor everything with BLS. So we have a little wire here, and we now connect this wire both to a microwave source, which you see here, and we need that for the parametric pumping process. And at the same time, we connect it to a battery for a DC current. And what happens with a wire where a DC current is flowing through, it generates an Ørsted field. Yeah, you know this. This is a wire, you have the Ørsted field around it, so it's a static field. And in this case, it's very useful because we can locally change the magnetic field. Everything's about inhomogeneities about this field. Yeah. In fact, we do it in a clever way because we do it with a pulse generator and a fast switch so that we can switch it on and off so we can do stroboscopic measurements. Yeah?
There is no resonator, so you use Stockton or something to get a resonance in microwave? Or?
Yeah, here's a resonator. Oh, sorry, no, it's not a resonator, it's a capacitor. Yeah. Yeah. In this.
Like I saw some other picture.
Yeah. This is very schematic and written. Good. So what are we doing now here, right? I mean, we have now the sample and everything is Bose-Einstein condensate. We have a central zone that is just here where we reduce the magnetic field. Yeah, you see it here. It's here reduced, but it's shown here as just the amount of reduction. And we have, let's call this the left zone and there's a right zone where we just have the undisturbed Bose-Einstein condensate. Now what we can do, so we can identify the boundaries of the central zone as the positions of the Magnonic Josephson junction. And now what we can do, we can observe the supercurrents, yeah, because again, same scenario as before, different areas, different fields, and therefore we should get a phase gradient, and therefore we should get the supercurrents. Do they interfere? That is a big question now. Do we get Josephson oscillations? And the answer is, let's check. Let's check with Brunel light scattering. So we put our laser focus just in here. So you see that here. And then we can measure. And what we see here now as a function of the same scenario here, as a function of time, we do the pumping. And then we need some time where the BEC is formed. That is just here after we switch off the pumping. Same story again. Yeah. And then we see suddenly here an oscillation happen, and we see a second oscillation happen. And with your eye of love, you even see a third oscillation happening here. Yeah? So we see oscillations, and so indeed, these supercurrents can interfere because everything is coherent. So we find the Josephson oscillations in a magnetic condensate. So I think that is a good proof.
Just a quick question to that slide.
Yeah.
It's a time-resolved measurement.
Yeah.
So you create your supercurrents, switch off, measure, switch back on.
Yeah.
To avoid heating from your measurement laser.
Yeah. Sure, of course.
Otherwise, you could argue
the
barrier because of the measurement.
So you can do many things now. You can, for instance, measure here the pumping. Let me quickly go through it because time is running. Again, if we do everything right, so if a magnetic trench is formed, we get the DC current. We did a reference experiment where we make a ridge, just opposite current, electric current direction, yeah. Then we increase locally the field instead of decreasing it. Nothing happens here, but here we see this nice oscillations, and the oscillations depend on the depth of the tunnel junction, yeah, in between. That is exactly what you would expect, yeah, because by the depth of your tunnel junction, you manipulate the phase, very simple. So we get that right here. Okay, so much about that. Now let's move on. Kinetic instability sounds complicated. It's something very well known in the Ukraine and very little known here in our Western world. I don't know why that is, Andre. That is something you might have to explain. What is kinetic instability? Well, kinetic instability is very trivial. We'll circumvent all these 4 Magnon scattering processes. Yeah, we circumvent all the. Is it okay? Problem? Okay. We circumvent all these 4 Magnon scattering processes, and we directly go from this parametrically excited Magnons at half the pumping frequency to the bottom. Yeah. So we take a Magnon here, and this Magnon, we undergo a 3 Magnon scattering process now. So this Magnon will, so one of the new Magnons will go down here, and the other Magnon will go up to this frequency. Yeah, you see that? This only works if you have resonance conditions, so you need to have some states here so that it really works. Yeah. Or in other words, the minimum condition is that the distance, it's a frequency distance between this state and the position of the condensate is half the frequency distance or energy distance between the pumping frequency and the intermediate frequency as half the pumping frequency. So it's a very special scenario. And if you do that, BEC is formed. Initially, we were very much trying to avoid this for the very simple reason, if we claim we get a Bose-Einstein condensate this way, you would immediately kill our paper, because you would simply say, oh, that is a coherent process. No surprise that you get a condensate, because you simply use the coherency of your microwave source, and in this 2-step process, coherency is maintained. Yeah, this would not work. Yeah. So, okay. But I mean, once you know everything is working, you can use it as another means to create a Bose-Einstein condensate. Already not with a free phase in this case. Okay, let me skip forward here. So, the question very often is, so what do we observe here? Is it really a Bose-Einstein condensate, or is it just a kinetic instability? What you could do, you could draw diagrams, and this diagram show you what is really happening. What we plot here is a parallel wave vector component and the perpendicular wave vector component. And then in these kind of diagrams, we can draw isofrequency curves. Yeah, that is nothing else than now taking the dispersion. Remember, dispersion is very anisotropic. And in order to better understand this anisotropicity, yeah, you simply can go to these kind of diagrams, yeah, parallel component, perpendicular component of wave vectors, and then you draw these lines where you have states with the same frequency. And I plot here 2 values. One is half the pumping frequency, where we generate the Magnons in the pumping process. And the other is just here the difference in the frequency you have seen before, omega pumping minus omega min. Yeah? And now, if we do so, we can create pumped Magnons just here at these green spots, what you see here. You see 2 green spots. If we take another scenario, the green spots might just sit here, or if we take another scenario, we get a green spot here and over there. Yeah, so that is where we pump the Magnons in our spectrum. Yeah. You see its frequency and of course also the direction of the wave vector and of course the amount of the wave vector anyway. And now we ask ourselves, for these scenarios, do we have kinetic instability or not? And the condition is very clear. We can get a kinetic instability if these pumped Magnons can decay into one Magnon going onto the blue curve and another Magnon going here to the minimum. The minimum is here. Yeah? You see that? Okay? Because then the energy conservation condition is maintained. Yeah? You have to add the values. Here is omega min. This is omega pump minus omega min, and that is omega pump over 2. Yeah? So you would like to get any state here on this omega pump over 2 curve to decay in two new magnons, one at omega pump minus omega min, and the other at omega min. Yeah? Then you have 2 times omega pump if you add it up. Yeah? Very trivial calculation. So this gives us now good insight what is happening. For instance, I get from this scenario to that scenario to that scenario simply by changing the field. Here you see the field values. Or what I can also do, I can simply plot the bias field, what you see here in a certain range. And then I can ask myself, do we get the conditions for kinetic instability? And the funny thing is, there are areas where there is no kinetic instability because you can't find the suitable states. And there are 2 areas where kinetic instability can happen. This is called kinetic instability area number 1, what you see here, and the kinetic instability area number 2. Here, the pumped magnons here are here at these positions. And here you see that now we have even a crossing here in this orange curve. So you have the pumped Magnon states here and there. So 2 different things. You can now do different things. You can calculate the thresholds. These are all threshold processes. You need a minimum amount of amplitude or intensity or number of Magnons in order to make this process happening. If you find the threshold here in orange color, and you can also ask what is the BLS signal if you measure it here at the bottom of the states. That is measured data. That is all measured data, by the way, and that is here this blue curve which you see here. So we have 2 areas where we can directly put Magnons into the minimum frequency position, so the position where the Bose-Einstein condensate should be. So you see again the richness we have. You have to make choices. Which area do you want to use? Which area do you better just try to avoid? And then you can do experiments. For instance, here it's 3 different cases. You do pumping, and then you monitor what is the decay here after that. There is always a logarithmic scale, so an exponential decay is just a straight line. With your eye of love, you can already see we have here two sections, one with a small slope, and here another one with a larger slope. And this you find on and on. You see it here again. Yeah, you see it here again. So these kind of things happen, and you can associate this with the 3 different scenarios. So, okay, then you can measure it with different heatings. And if you heat, something strange happens. You see, if you heat, the number of Magnons you have here is much less. You also see that the slope here is very much increasing. Do you see this here? Yeah. What is happening here? You might be confused, but it is just what you learned before, because we have the supercurrents. We cannot simply discuss this kind of stuff in terms of simple dispersion properties and so on. Yeah, we are creating here imbalances. So supercurrents set in. So we have an area here where we have the supercurrent. And here the density of the Magnons is too small in order to maintain a condensate anymore. And therefore, what happens is that here the condensate, that is gone, the remaining Magnons just decay. And if you measure the slope, we obtain data like Rostislav is measuring them every day. It's just a lifetime of Magnons in this particular system. So you see nice transitions we can get in between. So do we have supercurrents now in the case of a Bose-Einstein condensate, in the case of a kinetic instability? I had made this view graph in particular for Norbert, because Norbert is a mathematician. I thought I need to show a few more view graphs about the mass behind. I want to shock you with the mass. But it's actually not very difficult. What you have to consider is we have a very rich physical situation here now. We have Magnons, which we pump, and P means for the number of the pumped Magnons, okay? Yeah. We have Magnons in the gaseous states, just here. Yeah. We have Magnons near the bottom, that is this blue area here. We have magnons in the condensate NC. That are the magnons which are here. And now we want to develop the ratio. How does it develop over time? And in mathematical language, you have to write down rate equations. You have to solve them, as standard mathematical tools. And here are the rate equations. So we ask, how is the number of magnons here in the gaseous states changing as a function of time? For that, you need to write down the coupling to all the other reservoirs, and you need to put in also the nonlinearities on the system. If you have gaseous magnons, we have 4 magnon scattering. This means we have terms which are proportional to the number of magnons in the gaseous state to the power of 3. 4 minus 1 is 3. And all the other equations are just here. And at the very end, you also have to add here terms for the supercurrents, and of course for the damping. And if you solve it, you get the exact time dependence of all the kind of things. The answer is, if you do a calculation and if you take the experimental data, you can see that indeed you get a very good agreement between these kind of things. And these are the typical graphs. So we do the pumping. After pumping, usually the intensity shoots up very largely because all the gaseous magnons find their way into the condensate. And then the condensate uses magnons because you have the supercurrents. They transport away the magnons out of the laser focus where you are doing the measurements. And after a while, the density of magnons becomes too low to stabilize the condensate, and then you have the usual decay. So you get always these 3-stage processes here. And if you solve here these rate equations, that is solved actually without any significant free parameter in the system, so you get a very good agreement here between. We have done this a couple of years ago. So, okay. And the supercurrent is, as I told you, is very important in order to understand it. Good. So, this was the second difficult thing. And now I want to relax you a little bit by showing you an experiment where you can just relax, okay? And which basically explains a little bit better some part of what I was telling before. It's just for better learning for you. And these are the virtual magnons. You don't get too much distracted by the name, virtual magnons. What do? We do our standard experiments. We look into the dispersion. That is the dispersion of the backward volume mode. You remember, negative slope, minimum where the BEC happens, increase with higher wave vectors because of the onset of exchange interaction. If we do a measurement perpendicular to the field, we get the surface mode. So we get here just this kind of dispersion. This you all know. And now we do our standard experiment, but this time we drive the system a little bit harder. So we use more power. And if we do so, we suddenly get all kinds of exciting new excitations in our system. What do we see? We see here the Bose-Einstein condensate at the minimum position. You see that, we get some intensity here. We get other intensities here in between at certain spaces, at certain locations here within our dispersion curve. So we have wonderful accumulation phenomena. But why are the magnons accumulating here and at that position? That we now have to understand. You need to learn nothing new. You all know already what it is, but let me guide you through the answer. Let's just start with this one here. That is very simple to identify because that is just the frequency at which we pump the system. We pump the system with microwave photons, but since these photons enters a magnetic medium, it also drives the magnetization. And that is a forced magnon, if you will. I mean, if you have a pendulum, a standard pendulum clock, the pendulum goes with 1 turnaround per second, But if you drive it very hard with your hand, you can force the pendulum to go much faster, but the amplitude, of course, will be lower. Same thing here. If you drive a magnetic system very strongly, you can force it to any frequency. And if you like to use the word magnons, these are virtual magnons. Very simple. Okay, they are not a solution to the wave equation. So what happens next? What happens next is, of course, that these pumping magnons will decay into parametrically generated magnons. These magnons are here and there. I have to disappoint you because there's no intensity, but since you are all experienced Brillouin light scattering people, you know that at large wave vectors, the sensitivity of your Brillouin light scattering setup is 0. It doesn't work. You cannot simply see them. You are blind. Yeah? So you are blind to these magnons. You can only measure here in this area. So you can only believe that because you understand the physics, that you have a lot of magnons there. So what happens next? Well, of course, now, these are, of course, real magnons. What will happen next? Of course, Bose-Einstein condensation will happen. And here are the condensates, what you see here. You see also a lot of gaseous magnons here in between with some additional density. This we all do understand. What about the other peaks? Well, okay, you remember we had peaks over here, yeah? Some densities over here. What is happening here? If you look very carefully, you see this here is at 0 wave vector. And this here has about twice the wave vector of the condensate. And if you look into the frequencies, you will see the frequency is twice the frequency of the bottom. So what happens here is just a wonderful example of 3 Magnon scattering. Yeah? So 2 Magnons escape from the condensate and form a new Magnon with twice the frequency and twice the wave vector here in that area. Yeah? You see that? It might also happen that 1 Magnon from the left condensate and from the right condensate unify, and because the wave vectors are opposite, the new Magnon has 0 wave vector. That is the intensity you find here. So this is, in my view, the best demonstration how 3 Magnon, this is called confluence processes, can happen. And you get it because you drive the system very hardly. You remember we had more. So this is a confluence process. And here you see the conditions. Yeah, so the energy must be conserved and also the wave vector. But what about these Magnons? Now you have to solve a problem. Yeah? But it is not very difficult. You can make this Magnon by a 4 Magnon scattering process. And all you do is you take 2 Magnons, one here, and 1 Magnon over there, yeah? And this Magnon you let go down, and this Magnon you let go up, yeah? With the same amount, yeah? So that the energy is conserved. And the same applies to the wave vectors. You see this wave vector distance here is just the same like between here and the position of this peak. So a 4 Magnon scattering process. Is it too artificial what I'm telling you here? It sounds very artificial, isn't it? A little bit like scratching your head and then you come up with a solution and you really don't believe into the solution. Yeah. Yeah. There is a much deeper truth behind this. And the deep truth behind is, again, coherency. And I'm now really closing a little bit the arch over my entire lecture. Coherency matters. What you see, first of all, and this should make you wonder, is the intensity of these accumulation areas is about the same like here. Yeah? And if you're very good in nonlinearity, I wonder that Andre is not jumping up here because he should immediately tell me that is rubbish what I'm telling here, because I was naming this here 3 Magnon processes, and this now I call the 4 Magnon process. And Andre knows very, very well and doesn't kill me that the probability for a 4 Magnon scattering process is typically a factor of 10 weaker than for a 3 Magnon scattering process. But you don't see that in the data. Yeah? What is wrong here? What is wrong? Nothing is wrong. If we consider coherency, I will now make my second attempt to convince you how important coherency is. Number one is we have full phase correlation in the pair of parametric waves. So if we have a microwave photon here, and if it creates 2 Magnons here and there, these 2 Magnons originate from the same microwave photon. So they are phase correlated. Yeah? There's a very strict phase relations in between. Yeah, because the original Magnon just defines the phase of the 2 new Magnons. Yeah? 3 Magnon scattering processes in themselves are, of course, phase coherent. So we know this Magnon, we don't know what the phase is, but we know the phase of this Magnon is the same phase like here. If I use words, we don't know what the phase is, that is a kind of speaking you are known from quantum mechanics. We are coming close to quantum mechanics. Yeah, but we are not doing quantum mechanics here. So, okay, so these 2 Magnons have the same phase. Now, the BC, of course, has a different phase. We don't know what the phase is. But if this Magnon decays to this one here, and this one to this one here, these 2 processes, these 2 blue arrows are again phase correlated. Yeah? You see that? So what do we have here? We consider the pair of paramagnetic Magnons as coherent wave objects. Therefore, the 4 Magnon scattering process is phase enhanced. Yeah, so this process here is coherent, what we have here, yeah, because we start from the same coherent state. Yeah? So we have a phase coherent thing. And there is another rule: if you do multi-Magnon scattering or any time of multi-particle scattering processes, you gain amplitude by making this process phase coherent. Yeah, that is well known in quantum physics, in quantum optics. Nonlinear processes with quantum correlated input have higher efficiency. Yeah, the quantum people know it very well. But what I'm showing you here is it is nothing, it is really quantum, it's just classical wave optics. If you consider the coherency of your problem. Yeah. Normally, if you think about 3 Magnon scattering, 4 Magnon scattering, you always think about incoherent objects in your mind. But you have to keep in mind they can be phase correlated. And if you have phase correlation, you avoid destructive interference. Yeah? And in this way, you enhance the probability that the process takes place. Yeah?
So then could I ask a question?
Sure.
So if I just look at one Bose-Einstein condensate, everything you explained yesterday and to show it is actually Bose-Einstein condensate, I just need to explain local phases, right?
Yeah.
Vortices and everything is local phases. Wouldn't it be then a different way of explaining that what you look at here, what you explain and use the term phase enhanced, is it the global phase? Because also yesterday I was wondering, you have your 2 Bose-Einstein condensates, the global phase that each of them will have, are they imprinted onto each other? And do they come from the Magnons or not? So how could I understand that in terms of local and global?
You have to be very careful with the word local and global.
Sure.
Number 1, if you have a condensate, the condensate always happens at the minimum. What is the group velocity here? 0. Yeah, so the condensate doesn't move. Yeah, it sits there and it oscillates local. Yeah, it oscillates. Sorry.
It spins itself, right?
Yeah, but we always get 2 condensates, but we don't know what the phase difference is here in between, because each condensate is independent and has its own phase, and the phase is random, as we were discussing yesterday. Yeah, it's an order parameter. Yeah, so these don't have any phase correlation. Yeah, as different from these Magnons here over there, because they are connected to this microwave photon over there. Yeah, it is different if you go into wave vector space. Yeah, because these are, of course, at the same physical space, real space. Yeah, so one is oscillating here and the other is oscillating here, but the wave vector is different. So if you plot it on wave vector space, we are discussing here 2 separate objects. And we are fully in the range where we have transport phenomena now in the reciprocal space, what I was advertising at the very beginning. So we transport energy from here to another wave vector, to another wave vector. So we are moving now things around in a reciprocal space, as different from local space. Does it answer your question? Yeah. Okay. Then let's move on. So we get this. So what we have here is just a classical version of quantum enhancement. So we have it in our world. Good. We also have another process. This is dashed blue lines, but this is just the same thing like this one, only mirrored to the other side. So we can take these 2 Magnons, they are phase coherent, and we do a 4 Magnon scattering process where this Magnon scatters into that one and that one into that one. So we have 4 Magnons again, same process. Yeah, you just have to think a little bit more freely. As long as this entire system is coherent, this kind of processes can happen. Yeah. Good. So accumulation phenomena, we have it here. Let me now show you another another accumulation phenomenon, which I like very much, where you again can expand your knowledge now. And that is Magnon phonon accumulation. It's called bottleneck accumulation, and you will understand why it is called bottleneck. Now, again, you see the backward volume mode here. Again, frequency is a function of wave vector. But now we add a phonon to our system, just the usual transverse acoustic phonon, the most boring phonon you have in your system. Yeah, the one which you can excite with surface acoustic waves, for instance. So we have that phonon here, and if you have an interaction, and you always have a magnetoelastic interaction, then you get some hybridization here in this regime. I think you are familiar with this kind of things. Yeah, two modes cross, but since you have an interaction, a gap is formed. Yeah. Nothing else in there. You can write down, of course, the effective field. So again, we have the dipolar interaction, we have the exchange interaction, and we now add a term for the magnetoelastic interaction, and this gives us a full dispersion. Of course, if you now go on a computer, try to solve it numerically, you can do it, but of course the computer time is now very much increasing because the system is getting more complex. So you can understand this very, very well. We are interested in the transport phenomena. This is the name of our lecture today. Yeah, so let's see what happens. So what happens here in these areas? Okay, of course we can do an experiment that is Brillouin light scattering. You see again the backward volume mode here. You see the transverse acoustic phonon here for the experts. You work with different polarizations. Here for the Magnons, you obviously like a cross polarization. The phonons very often you get in different polarizations. It depends on the details of the phonon mode you are studying. Okay, so you can do this. We have seen Bose-Einstein condensation. That is just exactly as we discussed it. We do pumping. Here is the time. We wait. After a while, the Magnon gas condenses into the BC. We see the BC here. That is the weak pumping case. Yeah, that is well known. And if we now do the same experiment with higher power, we see suddenly another mode here. Yeah. We call it the magnetoelastic mode, or the MEM mode. And why is this happening? Because we now have to take this area. Let's just rotate it. Then you see this is now the wave vector axis. Here we get the BC. And here we get now the crossing regime. So what do we infer from the experiment? Obviously, we have another kind of accumulation happening here. You see this? Because we get all the Magnons here, which you see directly with Brillouin light scattering. So what is happening here? Let me explain it to you. We simply have our Yick sample, that is now the sample. We have here the stripe of copper where we do the pumping, and we put the probing spot of our BLS system just here at this point. Yeah. And now what we can do, we can measure, and what happens is that with a function of time, of course you have modes running in both directions, and if you do the pumping, you also create phonons. And if you are sitting here over the time, all the phonons which are sitting here at the boundary will cross here the center point, and therefore the intensity will increase. Very boring, very simple process. If you do the oh sorry, that was too fast. What is this? If you do the experiment, then you get these kind of pictures. You get the magnetoelastic modes here. You get some laser modes which are not interesting, and you get a gaseous phase here. And if you wait a little bit longer, you also see here the onset of the Bose-Einstein condensate. Very simple. You can also probe at a different space, different position like here. Now you collect only modes, magnetoelastic modes, which come from this side and which can collect all the Magnons which you have created in here. Yeah. Once again, you have a magnetoelastic mode. You feed these magnetoelastic modes with a parametrically excited Magnons. Yeah. And therefore, the intensity is increasing as these modes propagate now from the left side to the right side, and we are testing at this point. If you do so, what you get is a very asymmetric spectrum. because you know this is positive wave vectors, this is negative wave vectors. If we now measure here, we only get those modes with a positive wave vector because you have to travel across the pumping area in order to gain enough intensity, enough amplitude. Yeah. Okay. So we get an asymmetric spectrum. So be careful here, because asymmetric spectra, normally we talk about unidirectional properties and so on. Sometimes it is just the way you do the experiment. And if you have collective modes, or hybrid modes, which can collect energy from other modes, yeah, you can get this kind of scenario. So this happens. I like to call it the Magnon phonon cow. Yeah. Why Magnon phonon cow? You know how a cow operates. Yeah. You have to imagine how a cow operates. Assume this is a meadow. Yeah. And the cow decides to go to the other side of the meadow. Yeah. We are physicists. We know what it means. It simply means the following. The cow needs energy in order to transport herself to the other side. Yeah? A cow is heavy, so it needs a lot of energy. Yeah, energy is conserved, and therefore the weight of the cow will decrease if you go from here to there, yeah? Because it has to divert, weight into energy in order to move over. But you know what a cow does. Yeah? A cow is just mowing grass. Yeah? So the cow is eating the grass. So at the same time, the cow is running from here to there. It loses energy and it gains energy because it is eating all the grass. Of course, most interesting is which process is winning here. Yeah. And here exactly the same thing is happening. You have here modes, these magnetoelastic modes, which are partially magnetic, as magnons, partially elastic, which means phonons, yeah? So these modes are propagating, but they can now eat all these parametric excited magnons, yeah? And if there are enough, of course, they will gain weight, which means they will gain amplitude. And that is why I like to call this a Magnon phonon cow, because it grazes across a meadow of all the gaseous magnons you create in this scenario, yeah? Just mind, condensate is formed by getting some gaseous magnons into the condensate. And if there are many gaseous magnons around, then this is good for the condensate. So, okay, the grass is a greasing magnon cow. But what is the mechanism now? Why this does really happen? And that is something very funny. Again, what you see here is the crossing regime between the magnons shown here in dashed blue and the phonons shown in dashed red. You are familiar with both curves, yeah? I'm only showing here a very small part of the entire dispersion curve. We have to look into the scattering processes. You know, the leading term usually is just the 4-magnon scattering, which you see here, 2 incoming magnons, 2 outgoing magnons. And you have that certainly here on the right side here of this picture. So we call it the low branch. And so 2 magnons from here and there can scatter, and 2 magnons are coming out. Which means if we populate just this state here, let's just assume we do this, this population might simply just travel in the reciprocal space, of course, along this green line, yeah, because of the 4-magnon scattering processes. The same with the other branch here. This is also magnonic. So you can also have scattering processes, which you have here. You can have additional scattering processes because 2 magnons, for instance, from the green side, can scatter into 2 magnons on the orange side. Yeah? Every kind of 4-magnon scattering process can happen. So you can look into the probabilities. What is the probability? And now the funny thing comes. We plot now, we take a different dimension, we simply plot now the scattering amplitudes as a function of the distance from the crossing point. So here's the crossing point, yeah? And this is just the dimensionless frequency distance here in this regime. So what happens, these magnons here, they can scatter, but what you see here, these magnons are converting into phonons, yeah? And now magnons are strongly nonlinear, Landau-Lifshitz equation, phonons are linear. It's very hard to drive phonons into a nonlinear regime. Yeah? So this mode becomes more and more linear Or in other words, if you now plot the probability of these 4 particles scattering, I now should say 4 particles scattering, it becomes lower and lower the closer you arrive here at the crossing point, and here beyond there is no scattering intensity anymore. And the same for the other branch, for this orange branch, the scattering probability of the magnonic part here decreases because it becomes more and more phononic. And here in the middle, of course, you have a transition regime where you can cross from this side to that side, and it has its maximum very clearly at the crossing point of these 2 curves. Yeah? So these are the probabilities. What does it mean? It means that now if the magnons are coming, they are scattering, and they would like to follow this branch. But in order to follow the branch, there must be 4 particle scattering processes. And if these scattering processes are becoming increasingly forbidden because of the increasing phononic character of the modes, you do not get any further scattering processes. So what happens is these modes get stuck, or this intensity gets stuck, and we are talking here about accumulation of magnons in a virtual minimum. It's not a real minimum because you could just climb down the phonon branch, but in fact you cannot climb down in terms of number of magnons, because for climbing down you need higher order processes, 4 particle scattering processes in particular. And they are forbidden if it becomes too strongly phononic. So another way of accumulation processes which we have here. So we have the creation of a virtual minimum at the avoided crossing here of the system. You can look into the group velocities. Group velocities is something you can measure very nicely, because you can do space-resolved Brillouin light scattering, space and time-resolved Brillouin light scattering. You can look into the phonon velocities, which are large because the slope is large, and Magnon velocities are always lower. And if the slope is even 0, of course, then there is no velocity. And then you can do experiments. For instance, this is simply just now again the Yick film. Here is a pumping area very schematically shown. And we now can look what happens, and if we do an experiment, so we measure the position of the maxima as a function of time, we can determine here the velocities. Interestingly enough, we get 2 velocities here out. Yeah? So we have to find out what is happening here. One is, of course, the group velocity of the phonons. The other is the group velocity of the magnons. But there's even more happening here in the hybridization area. And for that, you can make these kind of experiments. Now, again, the Yick sample is here. And now there is no microwave antenna anymore. There's only a little inductive loop, which is good enough for this experiment. So we locally excite the system only here at this point. And then what we can do, we can again measure with BLS everything. And if we do a measurement as a function of time, we get this kind of population. Do you see this? Very rich. Yeah, at the very beginning, something is shooting up here in this direction. Let me start it again. Come on. So yeah, you see something is happening here and something is shooting up with a much larger velocity. So many things are happening here. We can take actually many of these kind of pictures. You see it here in this diagram. The colors are different because this was published in a different journal. And so if we now look here into the scenarios as a function of time, you see the time is running here in this way. So first something shoots up to the top and to the bottom, and a while later we see this other propagation in somewhat different directions. So many things are happening here. But if you understand it, you can fully describe the system. Why do we have this complicated thing? Another effect comes in, and that is caustic. Do you know caustics? Have you ever heard about caustics? Caustic is simply Poynting vector. I mean, you are creating all kinds of modes. The modes are propagating away. But you would like to know what is the direction of the energy flow. Yeah? Because, you know, if you have an anisotropic medium, if this is a wavefront, yeah, the wavefront usually goes like this, you think. Yeah, you can be totally wrong, because the wavefront might also run here in this direction. Yeah, you see? Which means the Poynting vector is different from the wavefront. The wavefront is defined by the wave vector. So this can be the wave vector. this can be the pointing vector which tells you in which direction the energy flow happens. Yeah? Very complicated, but in fact it's very simple. Because what you need to do is simply just think a little bit. Let me skip this part because I was already telling it. But what you have to do is you just have to look into your dispersion. Here is the dispersion in full beauty. You see here these two axes are the wave vectors. We are now making a three-dimensional plot. Vertical axis is the frequency. You see the dispersion. You see how anisotropic the dispersion is. We have two sheets because here we have this crossing. Yeah? Here the character is phonon-like. Here's the character is phonon-like. Here's the character is Magnon-like. Yeah? Can you identify all these kind of things, the dispersion you have seen before? Yeah? Christina, you are somewhat looking worried. Yeah? Only take a cut, then again you see here this avoided crossing regime you have seen before. Yeah? Just this one here. Yeah? This one here, as you have seen before. Yeah? You just find it exactly here again. Yeah? And now I expand it, since I do not only show it for the wave vector parallel to the field, but also the perpendicular components, and we get a three-dimensional picture. Yeah? And we get the two sheets, because this line expands to a sheet if you allow also for the wave vector in the y direction, and you have to solve just the equation of motion, then you get this kind of things. For simplicity, let me take away this part. And now what we can plot is iso-frequency curves. Better to say iso-energy curves, but in our world it's iso-frequency. It's the same thing, yeah? Just h bar in between. And these curves are very interesting because the pointing vector is always radiated perpendicular to the iso-frequency curves. So we just have to look, where do we have parallel lines, such here, yeah? Here the pointing vector will point in this direction. You see that? Yeah? It's at an arbitrary angle, something like roughly 45 degrees or 60 degrees, something like that. So that is where the energy goes. Yeah? So with that, we can understand what is happening. So the energy goes always, the flow is always perpendicular. We now have to, of course, integrate over the different parts what we have here. And if we do so, indeed, we find here, this is now the angle here in degree. We find peaks at 0, that is the quasiphonons, this thing here. And we find the quasimagnons here at an angle of 59 degrees. That is roughly here, this direction you just have seen. Yeah, so we can see that. And of course, this makes it a little bit more complicated, but this we can understand now very nicely, that we can really harvest this kind of thing. You can do numerical simulation. I will skip this part. I have 5 minutes, Andre, is this correct? So I will devote the last 5 minutes now to do something useful with it, and that is quantum computing with Magnons. But of course, it is classical quantum computing. And the idea behind is very simple. We use our BCs. Our BCs are wave functions where we can freely choose the phase. So we can generate qubits out of them. Yeah, the addition of two wave functions is a qubit. You all know this. Yeah, we need two states, a plus state, a minus state with well-defined amplitudes, and a relative phase between them to form a qubit. And we use the two condensates. We know now how to make them and how to operate them. And I will show you that indeed something good can be made with it. You know, in all this qubit calculus, you plot them here on the Bloch sphere. Yeah, so North Pole is only a condensate on the right side. South Pole is only a condensate at the left side or negative wave vector side. If you have both equally filled, you are on a state somewhere on the equator, and the relative phase in between will tell you where on the equator you are. Yeah.
Maybe just in the off chance I'm wrong here. You said before you do not know the phase between left and right bosons and condensate. How can you define a Bloch sphere if you do not know your qubit state?
Because I know the phase, because I set the phase.
You can set it.
I will show you.
Okay.
I show you. Yeah, the trick is I will use the wave function of the condensate. Okay. The wave function is characterized by two parameters. One is the amplitude, and the other is the phase. And I will show you ways how to set the phase, and show a way how to set the amplitude. And this way I can define the qubit. Yeah, okay? Good. That is what we have to do. But first of all, you know, qubit is very often just represented by a point here on the Bloch sphere, very convenient to do. And exceptional points are the North Pole and the South Pole. So why is this important? Well, I think we can do quantum computing with classical magnonics. And the answer why I think we can do it is this work by mathematicians. What you have to ask is, what do I need? For instance, if you want to have interaction, in quantum mechanics you have entanglement. There's also a classical version of entanglement, which is not really just the right thing, that is non-separability of wave functions, but this is only a sophisticated detail. Noise is different in quantum mechanics. We have quantum noise, we have classical noise. But now if you ask, what are the most important algorithms I would like to use with my quantum computer? And this is either the fast Fourier transform or some sorting algorithms. And let me just focus on this algorithm for fast Fourier transform. The good news, and this is work back in 2007 by these mathematicians, they show that in the classical world you can define algorithms for qubits which scale polynomially, non-exponentially. And which is the most important condition in order to have fast quantum computing. With classical computers, you cannot write algorithms which scale polynomially, so they always scale exponentially. So if you increase the system size, the computation time just starts to diverge. But if you can show that you have an algorithm which does polynomial scaling, then you are safe. So all one needs to show now is that with this kind of wave-based computing, you can indeed realize such a system. It has been shown actually in optics, and I will show you that with our Bose-Einstein condensates we can also do it. We have two tasks usually to fulfill. One is initialization of the Magnonic qubit state, answer to your question. And number two is how can we move the Magnonic qubit state on the Bloch sphere, which means how can we realize unitary transformations. Well, we have wave vector selective parametric pumping. I will show you how it works. And the phase is very simple. We simply can seed the BEC while it is forming by a very weak microwave field. Then the BEC will adopt the phase of the weak seeding microwave field. So that is an easy job. Here, that is actually something which goes back to Andre, because Andre is a master of Magnonic crystals. We can use Magnonic crystals in many ways. I will show you a Maxwell crystal, which is even nicer. For instance, a Magnonic crystal can be created just using YIG, having some wires and putting a DC current through the wires, okay? That is a classic Magnonic crystal, And what happens is you get Bragg reflection if the wavelengths of your spin waves just matches the distance between these wires. Very, very stuff. And gaps open, But you can do more. And then actually what happens is that you get reflections of the spin waves where you have the gap positions. And you even can show that you can obtain Rabi oscillations. So that is old work by Andre, I'm referring here. That actually you get two condensates. And if you put these two condensates on a Magnonic crystal, you'll see that the intensity oscillates between the two BECs. Here you see it just very nicely, Rabi oscillations, because of the coupling via the Magnonic crystal, just as a side remark. So this works. But you can do more, and now I show you a Maxwell crystal. Maxwell crystal is very simple. Again, you have the same geometry, but now you put microwave signals through the crystal, okay? And you do it in a way that each line here, each wire, gets a different phase. You need just a couple of coupled microwave generators. So this has a phase 0, and then this should have the phase pi over 2, pi, 3 pi over 2, and then 4 pi over 2, which is 0 again. You see this here, And now what happens if you do so? Well, you do a very simple numerical simulation that is really for the graduate students. put your Maxwell equations on your computer, let the simulation run, nothing else than Maxwell simulation. For this kind of scenario, what you see here is just the wires. The wires, they run into the plane. Yeah, you see, okay? So you just have a cut here through the wires. And now if you do the simulation, look what it looks like. It looks like a wave, isn't it? Yeah, it looks like a wave. It's an electromagnetic wave. What does it mean? In our usual language, it simply means that if we now do Bose-Einstein condensation in this scenario, we pump with photons who have a large wave vector, have a finite wave vector. So we give the photons an artificial wave vector via this Maxwell crystal. Yeah, you see that? Yeah. But what happens now if you do Bose-Einstein condensation? All these photons will create magnons, which are just sitting here in this half part, and only this BEC is filled. Yeah, a very nice way how to initialize a state which we called before the North Pole state. Yeah, and we can actually, what is this? We can actually do numerical simulation of the entire process, and indeed we only fill one of these BECs. So we can initialize any qubit state we wish to, yeah, with this method, and as well as with phase seeding. And then we have to show that we can do the single qubit protocols, moving a qubit around. And indeed, this can be done by applying fields, by applying field gradients. I have no time, unfortunately, to go through all the details, but I think it is very clear that this is not possible to do. We can generate a Hadamard gate, and if you have a Hadamard gate and a CNOT gate, you can basically program any kind of logic operations you would like to have, just the standard knowledge, so this can work. Finally, you have to couple the qubits, but again, this is very easy because, for instance, you can have two BECs, you can have a gap in between. That is a Josephson scenario you just have learned half an hour ago. So this works. Or you can simply make these two things. You can put a control line where you put a current through. You can separate the BEC into two parts, the right part and the left part. And again, some wires here for the measurements. Or you can even work with so-called flying qubits by connecting two condensates with the three wires which allow for a phase coherent transport of information between the wires. These are just wires which pick up the BEC state, yeah? And the microwave current which is flying through the wires generated by the BECs, of course, carries both the amplitude and the phase of this BEC and can couple it to the other BEC. So that is also possible. Now you have everything: initialization, manipulation, and coupling. And now you are ready to build your quantum computer. Okay. And with this, I am at my end. So here's just a summary of what I showed you. So thank you very much for being so patient to listen for me for the two lectures.